You will recall that there are two sampling models we can use, a model of homogeneity or a model of association. And I focused in the last topic on the model of homogeneity and comparing proportions among k conditions where k could be any number. You could have 2 groups, 3 groups, 4 groups, any number of conditions in which you can compare groups. We can compare them with an omnibus test, testing for the equality of proportions, or we can test them with multiple comparisons, in which we look at more specific information. What we did not do last time is look at the model of association and how to analyze the data from that model. We're going to do that now, but further, what we're going to do now extends to both models, the model of association and the model of homogeneity. This method allows us to actually look at a categorical response variable in a model form. You'll recall that we have a general linear model when we have a quantitative response variable in which we model the response as a function of explanatory variables that can be either categorical or quantitative. Well, the method we're going to use now, called logistic regression, allows us to model a categorical response variable as a function of explanatory variables that can be either quantitative or categorical. Now, what we're going to do in this topic is give you a flavor for logistic regression, rather than have you actually know how to use logistic regression. I look at this as having two outcomes. One, your understanding of the existence and the basic ideas of logistic regression, so that if you ever encounter a research situation that could be handled with logistic regression, you'll know about this. And second, when you read research, I want you to be able to read with understanding. So I'm deviating from our usual idea that we'll learn a method so that we can actually apply it in our research, instead confessing that you will not be able to apply this in your research until you think on it further, practice more, read more, or get more formal training. So in this course, I don't want to leave you without any understanding of what to do with a categorical response variable, which is why in the last 2 weeks we take on categorical response variables, but at the same time, I'm admittedly only giving you enough to get the general ideas. So with that preamble, let's talk about logistic regression. I've subtitled this the prediction of category. Why? Well, when we have a response variable that we predict, and that response variable happens to be a categorical response variable, what we're predicting is not an amount, but a category. So this is the prediction of category. The purpose of logistic regression is to predict or account for a response based upon known explanatory variables. The response variable is categorical, and the explanatory variables can be categorical and/or quantitative. Categories are predicted. The predictor value is going to be assessed or estimated, and this will help us understand something about how the predictor value plays into the category that people respond to. Now, the typical use is with a dichotomous response variable, but of course we sometimes have categorical variables that go beyond yes, no, true, false, success, failure, or other dichotomies. So there are extensions that exist for k-level categorical variables, both ordered and unordered. But in this class, we're going to just introduce this with a dichotomous response variable. This can be used with either sampling model, the model of homogeneity, in which you sample from separate populations and measure on one categorical response, or the model of independence, in which you sample from a single population, but then you measure individuals on multiple variables. Here's an example that we'll use to set the framework for learning about logistic regression. A researcher randomly assigned 100 students to control and treatment conditions. Members of the treatment group received modified educational experiences. In other words, they received an educational intervention that I'm not describing here. At the end of the semester, the same test was administered to all 100 students, and here you see the outcomes. So what do we have as a response measure here? We have an outcome category, either fail or pass. What is the explanatory variable here? It is the condition that each student is in, either control or treatment. Control being traditional educational experiences, and the treatment being some modified experience. In this case, the explanatory variable, just like the response variable, is categorical. So we have two categorical variables, but one is the response and one is the explanatory. Now, just looking at these data here, it looks like the treatment's working. Why? Because out of the 50 individuals in the treatment condition, 40 of them passed, whereas in the control condition that also had 50 individuals, 30 of them passed. Let's look a little more closely at the statistics that we commonly use in logistic regression to discuss these kinds of outcomes. We use conditional probability, and even more commonly, we use odds. Conditional probability is the probability of obtaining a specified outcome if you're in a specified condition. You're used to the idea of conditioning. We've done that both with a quantitative response, and we're doing that now with a categorical response. Conditioning means that you're calculating the statistics conditioned on one level of some variable. So here, if we're going to calculate the probability of a pass conditioned on the control group, then we're going to take just the 50 people in the control group, calculate the 30 out of 50, and our estimation of the probability of passing is 0.6 or 60%. The notation here is read as the probability of pass conditioned on the control. Similarly, the probability of pass conditioned on the treatment is 40 out of 50. Of the 50 individuals in the treatment, 40 of them passed. So we get 0.8 or 80%. But we can also measure this with odds, and odds are what we usually use when we have a categorical response variable. Odds are related to, but not the same as, probability and proportion, and thus they take a little bit of getting used to, especially when you're seeing them for the first time. People who work with categorical response variables get so used to odds that they can think of them as easily as they can think of proportions. The odds of a specified outcome is the ratio of the expected frequency of that outcome to that of another outcome, and these can be estimated with observed frequencies. So here's how we calculate the odds of passing for a control condition. There were 50 individuals in the condition. 30 of them met our criteria and passed. The other 20 did not. So the odds of passing are 30, that is the number who passed, to 20, the number who did not pass or who failed, and that can be simplified as 3 to 2. So we say the odds of passing for the control condition are 3 to 2. That means for every 3 people that pass, 2 people do not. Similarly, the odds of passing for the treatment condition are 40 to 10. or 4 to 1. That means that 4 people pass for every 1 person that does not pass. So when dealing with a categorical response variable, our descriptive statistics are to estimate either conditional probability or, more commonly, the odds.